So, welcome to Electrochemistry as part of Chem 0902. Almost all reactions studied in chemistry involve the transfer of electrons. Now, of course, when an atom or a molecule gains electrons, the species is said to be reduced, and the process is called a reduction process or a reduction reaction. This is accompanied by reduction in the formal charge on the species. That is, the species become negative. Conversely, when a species lose electrons, the species is said to be oxidized, and the process is called oxidation, or is said to be an oxidation reaction. Of course, this is accompanied by an increase in the formal charge on the species. So these things are important for us to understand as a foundation. Now recall from the first law of thermodynamics that matter, charge, and energy, etc. must be conserved, as indicated by the statement of the first law of thermodynamics. Therefore, oxidation and reduction processes must occur simultaneously. Redox processes, this is called. What this means is that if there's oxidation, if something is oxidized, then something else must be reduced. They must occur simultaneously, because you cannot have an increase in charge on one species and there is no decrease in charge on another species or decrease in formal charge. So if something gains electrons, then something else must have lost those electrons. So there is conservation of charge. Right. So that is important, and that from the first law of thermodynamics, that is indicated. Now, electrochemistry really looks at the behavior of ions in solution, and also the passage of current through an electrolyte solution, and really what happens during that process. Now, thermodynamics and kinetics of redox processes can be homogeneous, can be heterogeneous. Now, an electrolyte is a substance which completely or partially dissociates in solution and thus can conduct electricity. Now, let's look a little bit deeper into electrochemistry. Now, first of all, there are two types of electrochemical cells. You have what we call the electrolytic cell, and we have also the voltaic cell. Voltaic cell is also called the galvanic cell. Now, the galvanic cell, which is also called the voltaic cell, stores electrical energy, right? For example, and a good example is that would be your cells, like which when combined with a few others are called batteries, right? So, for example, your cell phone batteries, which are made up of a few cells. These are galvanic cells that make up your cell phone battery. Remember, a battery is a combination of two or more cells. Now, the thing is about a galvanic cell, what you have is a spontaneous reaction taking place, and in so doing produces charge. That is what happens in a galvanic cell. Right? So the reaction in a galvanic cell is spontaneous. That is the main point to take away. It is spontaneous. And whilst this spontaneous reaction is occurring, it is producing charge. A good example of a galvanic cell type reaction is when a piece of zinc metal is immersed in a copper sulfate solution. And then after a time, what you realize is that the copper sulfate solution starts to become pale. And then the zinc metal starts to become dark or become soft and mushy, as can be seen from the diagram on your right. And this is what we call galvanic displacement. What happens, of course, is that the copper is deposited on the surface of the zinc, whereas the zinc metal is dissolved. And we'll talk some more about this particular reaction in different forms. Of course, now we have the electrolytic cell, as mentioned earlier. The electrolytic cell, the main thing you must understand about the electrolytic cell as compared to the galvanic cell is that in the electrolytic cell, what you have is a non-spontaneous reaction that is being driven by the input of charge. And so I have here that the electrochemical reaction does not proceed spontaneously. So it's a non-spontaneous reaction, and it is being driven by the input of charge. For example, the production of aluminum. in producing alumina, which is aluminum oxide, is converted to aluminum metal. Now, this process is spontaneous. Going from aluminum oxide to aluminum metal is non-spontaneous. And so what you have to do now, you have to force the reaction to happen by pumping charge in for this to happen. Right? So it requires energy. And these are just some, simple examples that I could have, picked up. So you could just create an image in your head. Now, let's look more into the galvanic cell, which is the point of this particular lecture. Now, let's say, as we showed earlier, you dip a piece of zinc into copper sulfate solution. Now, the resulting reaction is a spontaneous deposition of copper metal and the formation of zinc 2 ions. So the zinc metal gets converted, as you can see from the blow up on your right, that the zinc 0, right, the zinc atoms will be converted to zinc 2 plus, right? And when they do so, the electrons that the zinc atoms will lose in going from zinc 0 to zinc 2 plus will go into the copper metal or the copper ions and convert them to copper 0. Hence, they are deposited on the surface of the zinc metal. And you see more of this reaction. So this insert basically gives you an idea of what is happening at the surface of the zinc metal. Right? And as I said just now, the zinc atoms, right, have no charge. Firstly, they are not charged. These will get converted to zinc 2 plus. And the copper ions in solution will migrate to the surface of the zinc metal, where they will collect 2 electrons each from the zinc atoms to form copper 0. That is, the 2 plus charge will be neutralized. We'll speak more about this, but this is just to introduce you to what is going on with that galvanic displacement reaction. Now, in a galvanic cell, you have 2 situations. There are 2 possibilities, right? Situation A and situation B. Now, let's say you have a piece of metal. Let's say that piece of metal is zinc, or let's just call it metal X. If you dip that piece of metal in a solution of its salt, for example, let's say you're talking about zinc, and you dip a piece of zinc metal into, let's say, zinc nitrate solution, there are 2 possibilities represented by situation A and situation B. Situation A. That possibility is where the metal atoms inside the solid metal can come out into solution, leaving behind their electrons, as indicated by this black arrow which is pointing upward, right, with the minus on it. So the zinc or the metal atoms will go out into solution, leaving behind 2 electrons each. That is, they will become 2 plus in terms of charge. The fact that the atoms have moved from a charge of 0 to a charge of 2 plus, that is, they have formed ions by losing 2 electrons, that is called oxidation. So that's an oxidation reaction, right? In situation A, as indicated by this equation below. Right? In situation B, the other possibility is that metal ions in solution could migrate to the surface of the electrode, right? The lattice, and remember what the metal is, or the electrode, is a lattice, or which is an orderly array of atoms, right? So ions in solution could migrate to the surface of the metal, where they can collect electrons. And once an ion collects electrons, right? Once an ion gains electrons, that is called reduction, as defined earlier. So metal ions in solution can migrate to the surface of the electrode, where they can collect electrons, and therefore we say that they are reduced. So they are converted from, let's say the ions in solution were 2 plus. If they collect 2 electrons, then they become 2 minus or 0. What do you think? 2 plus, and you have something that has 2 positive charges on it, and then you add two negative charges, what do you think will happen? Will it go to 2 minus or will it stop at 0? And I'm telling you that it will be 0. Right? 2 plus, and you add 2 minus to it, you end up with 0. So the ions in solutions, the ions in solution, I should say, when they go to the electrode surface and they collect these 2 electrons, if these ions are 2 plus and they collect 2 electrons, they will go to 0. That is, they are reduced, so they become neutral, right? And so the ions, have now been converted more to a solid, as indicated by the equation beneath situation B. These are the two possibilities of what can happen when you immerse a piece of metal in a solution of its salt. And I'm going to tell you that in a galvanic cell, both of these situations occur, right? Because you'll realize that a galvanic cell, as indicated here, is arranged in such a way that you have two, what we call half cells. So we call these half cells. And in each half cell, you have a different type of reaction occurring. You have one where situation A is happening, as indicated earlier, and one where you have situation B is occurring. Let's say we have a galvanic cell arranged where we have copper metal, which is on our right, is immersed in a solution, let's say copper nitrate solution. And then on the left, we have a piece of zinc metal immersed in something like zinc nitrate, right? And we have to use what we call a salt bridge, and I'll explain to you why the salt bridge is of any importance at all. Then what you have is that at the zinc electrode, what you have is zinc atoms going into solution, leaving behind 2 electrons per zinc atom. So every zinc atom that goes into solution will leave behind 2 electrons inside the zinc metal. This will cause a buildup of negative charge inside the zinc metal. Those same 2 electrons will travel around an external circuit, right? They will travel around an external circuit and eventually arrive at the copper metal. And at the copper metal, or what we call the copper electrode, these 2 electrons will be collected by copper ions in solution. So copper ions in solution will go to the surface of the copper metal, where these 2 electrons will reduce these copper ions to form copper solid, which will stick to the surface of the copper electrode. Therefore, the copper electrode will eventually become fat, or you say it will increase in mass or size. Just to go back to the zinc metal or the zinc electrode, think about it. What do you think will happen to the size of the zinc electrode over time? Over time, of course, because the zinc electrode is continuously losing atoms because its atoms are being converted to ions, the zinc electrode will decrease in size, right? As you can imagine. At the copper electrode, why is the copper electrode positive? Why is the copper electrode positive? It is positive because it is continuously losing electrons to the ions in solution, as indicated by the insert on your far right. The electrons inside the electrode, these electrons are coming out of the electrode and are being accepted by copper ions in solution, and which of course are being reduced because that's a reduction process. Now, what is the importance of this salt bridge? What is this? The salt bridge is very important. The salt bridge not only connects the 2 half cells electrically, but think about this. If in the zinc half cell, which is on your left, zinc atoms are being converted to zinc 2 plus ions. So you have a flood of zinc 2 plus ions going into solution, right? But when you started the reaction, you had a balance of negative and positive ions in solution, right? Just before starting the reaction, there was a balance of negative and positive ions in solution. But a few minutes after the reaction has started, what you have is a situation where excess zinc 2 plus ions are going into solution. What do you think will eventually happen to the charge on the solution? The solution will eventually become positive, right? Right? The zinc half cell solution will eventually become positive because there's an excess of positive ions going into solution. These positive ions are coming from the zinc electrode. So that solution will become positive. Now that is a problem. Let's look at what happens in the cathodic half cell, I should say, which is on the right, the copper half cell. What you have is a situation where copper 2 plus ions are being converted to copper 0. They are being reduced. They are accepting 2 electrons, and so they become neutral. Therefore, the question remains, what happens to the negative ions that were in solution to neutralize, that were keeping the copper 2 ions electrically neutral, or the copper nitrate solution neutral in terms of charge? There will be a buildup of negative ions in the cathodic half cell because the copper, the 2 plus ions are being removed. They're being converted to 0 in terms of charge. And so there's a buildup now of excess negative ions because the 2 plus ions are being removed. So a lot of negative ions are being left behind. That will cause the cathodic half cell to become overall negative. Now, this is where the salt bridge comes in, because the salt bridge is composed of a strong electrolyte, which is made up of ions that are, fast moving. They move swiftly in solution. For example, sodium chloride or potassium chloride or potassium nitrate. Because the salt bridge is made up of these ions can diffuse, or they can migrate to the 2 half cells and therefore maintain charge balance. For example, in the anodic half cell, that is the zinc half cell, negative ions can migrate over into the zinc half cell to neutralize the buildup of positive charge that is being produced in that half cell. For the cathodic half cell, that is the copper half cell, positive ions can migrate to that half cell. Okay? And these positive ions will now help to create a charge balance with the excess negative ions that were left behind. So that is the importance of the salt bridge. It maintains what we call electroneutrality, alright, or charge balance, and it also connects the 2 half cells electrically. Now, if you insert a voltmeter in, as seen here, for copper and zinc half cells, which come together to make the overall cell, what you will find is that you will get a potential of 1.10 volts, provided that both solutions are 1 molar and that the temperature is about 25 degrees Celsius. Now, what you can see from this diagram is that at the anode, oxidation occurs, right? And the anode is negatively charged. The zinc electrode will be the anode, and it's negatively charged, as explained earlier. The cathode, which is the copper electrode, is positively charged, and we explained earlier why it is positively charged. At the cathode, you have reduction occurring, electrons being collected by ions in solution. Right? So the anode is the site of oxidation, whereas the cathode is the site of reduction. And that is important to note. It is also important to note, as discussed earlier, that electrons flow from anode to cathode. Alright? Oh, I think in my anodic half cell, I have one of my zinc ions with the improper charge. I need to fix that. Right. So this is basically how the galvanic cell work. Now, there are more details that we need to get into. Now, let's talk about half cell cell potential and reduction potentials. Now, if we isolate two species in the electrolyte and set up an electrical contact, if both solutions are 1 molar and the pressure is 1 bar and the temperature is about 25 degrees Celsius, the cell potential, that is the potential that you read on the voltmeter, is said to be the standard cell potential, right? Once the solutions are 1 molar and the pressure under which you're doing the experiment is 1 bar and also the temperature is 25 degrees Celsius, then the potential that you read on your voltmeter is said to be the standard cell potential. And of course, we should know that the cell potential, right, is made up from contributions of the two half cells. Right? That is important, and we will say more on that. Now, for any electrochemical cell, it is possible to write what we call half reactions, which are associated with the processes occurring. And you saw those that I wrote for the copper half cell and also the zinc half cell. Now, of course, different pairs of half cells give different overall cell potential values. Now, we can use cell potentials to quantify the tendency of a half reaction to go in the oxidation or reduction direction. So the cell potential, right, and also the half potentials can give us an idea of the tendency for a reaction to go in one direction, oxidation, or the other direction, reduction. Now, how do we arrive at a value for a particular half reaction? How do we get a potential value for just one of the half cells? How is that possible, seeing that the overall cell potential, which is what you would read from the voltmeter, is a contribution, right, is made up of contributions rather from both half cells. Now, we'll discuss that now. We choose a selected half reaction as standard reference and compare all other reactions. So that's exactly how we'll do it. Right? So if you want to know the potential produced by just the zinc half reaction, you need to compare that to what we call a standard reference electrode. And you'll see how that works. Now, the standard reference electrode that we will look at is what we call the standard hydrogen electrode, which is called the the acronym is normally SHE, S-H-E, standard hydrogen electrode. Now let's look at how the standard hydrogen electrode works. Now, the standard hydrogen electrode, as you can see, a diagram of it is placed on the left of this, on the right, I should say, of this slide. Well, what you have is hydrogen gas, right, going into a tube pointing downward at 1 bar pressure, and then you have a piece of platinum, metal which is coated with finely divided platinum, just basically particles of platinum, and the solution should be a 1 molar acid solution. Now, the reaction occurring is designated to have a contribution in terms of potential of 0.00 volts, meaning that it does not contribute. So if you should prepare a galvanic cell, and one of the half cells should be the standard hydrogen electrode, then that electrode has a contribution of 0. So the potential that you will read on the voltmeter will be only due to the metal that you are trying to investigate. So this cell does not contribute a potential value, and this is a designation that the scientific community has agreed on. So this one does not make a contribution. So if this is a part of the cell, if this, and I'm talking about the SHE, if the SHE is one of the half cells in the voltaic cell, whatever you get on the voltmeter is due to the metal that you're investigating. Right, and this is, normally used. No, first thing you have to understand is that the SHE is defined as the anode, and the cell potential measured with a high impedance voltmeter. Right, so you want a high impedance voltmeter, high resistance voltmeter, that is. So the voltmeter does not use up any of the potential that is being generated by the half cell in question. So of course, remember that the SHE is designated as the anode. So the metal to be tested must be designated therefore as the cathode. That is, that metal is being reduced. So the value that you get is the reduction potential value for that metal that is being investigated. Now, the reaction that occurs in the She, since the She is designated as the anode, is where hydrogen gas is being converted to hydrogen ions. That is, losing 2 electrons to produce also 2 H plus ions in solution. Now, the reaction, of course, like as mentioned earlier, is assigned a value of 0.00 volts. Thus, we have a quantitative scale for electrode potential. So all electrode potentials, which are reduction potentials, are measured relative to the She. And of course, the She is our universal reference electrode. So any potential, as mentioned, is due to the cathode, which is the metal to be tested. Now, calculating cell potentials. Now, generally, when you arrange your galvanic cell, you will have 2 half cells, the anodic half cell, right, or the anode half cell, and the cathodic half cell. The anode is negative, cathode is positive. The anode is the site of oxidation, the cathode is the site of reduction. And of course, you have to have your salt bridge. Okay. Now, to calculate the potential for a cell, it is just like calculating any other thermodynamic parameter. Alright? And you'll see what I'm talking about. Now, look at the direction of flow of electrons. We already explained that electrons flow from anode to cathode, and we explained why electrons are generated at the anode and will flow to the cathode. Now, we can ascribe an initial and a final place or state for the electrons. The initial state would be the anode because that's where they are generated, and the final state will be the cathode because they move from anode to cathode. Okay? And therefore, for any thermodynamic parameter, you'll remember that delta X is equal to final minus initial. So if you have, in other words, if you know the potential for the cathode, which is where the electrons end up, and you know the potential for the anode, which is where they start from, then it is cathode minus anode, which is equal to the cell potential, which is the same thing as delta E, change in potential. So the cell potential, that is the overall potential generated by the cell, that is the potential that you will read on the voltmeter, can be calculated by just saying E cathode, that is potential of the cathode, minus E anode. And that will give you the potential of the cell. Now, let's look at an example. Let's look at an example where we are using the She to check the potential or the reduction potential of a piece of copper metal. Remember, the She is always designated as the anode, and the metal to be tested or to be investigated is designated the cathode. Okay. So if we combine the copper electrode, right, with copper sulfate solution with the She, then of course at the anode we have hydrogen gas being converted to hydrogen ions because that is the reaction that occurs at the She. And then at the cathode, we have copper ions in solution being reduced to form copper solid because we know that is what happens at the cathode. At the cathode, reduction occurs. That is, ions in solution get converted to solid, right, or gets reduced. Right? So copper 2 ions accept 2 electrons and become copper solid. That's the anodic reaction. That's the cathodic reaction. Right? That is what occurs at the cathode, reduction. The overall reaction, if you combine those 2 half reactions by cancelling away the electrons and adding the 2 equations, which we will get into in more details later, you end up with copper 2 plus aqueous plus hydrogen gas going to give you copper solid plus 2H plus aqueous ions. The change in potential, which is the cell potential, is equal to cathode minus anode. Remember, for the She, the potential is 0.00 volts. Therefore, the cell potential will be due to copper alone, because the anode has no contribution. And so E cell, when you have the She as the anode, is equal to just the potential due to the cathode. Now, if the copper sulfate solution or the copper nitrate solution, alright, is 1 molar, the measured potential difference is plus 0.34 volts. Now, this is what we call the reduction potential. This is the standard reduction potential for copper, 0.34 volts. Why is it called the standard reduction potential? Well, remember the copper, right? The copper electrode immersed in a copper salt solution was made the cathode. What happens at the cathode? Reduction occurs at the cathode, and oxidation occurs at the anode. But the anode was made to be the She. The She has no contribution. So when we said cathode minus anode, since the She is 0, right, then the cell potential is equal to just the potential generated by the cathode. And the potential generated by the cathode is due to reduction of copper 2 plus ions, because that is what occurs at the cathode. Now, we will discuss some other stuff in our next lecture, or in the part B of this lecture.